is Pam Haas. I'm the Deputy Director of Strategic Initiatives at CDT, and I'm just going to be the host for today's session. We are recording it, so thank you whoever started that. If you have a question at the end that you wish to not be recorded, we can easily turn off that at the Q&A. We're primarily just recording the presentation part of today's event. So thank you for being part of the community of practice on AI. The purpose of this is to foster awareness of AI and AI-related projects throughout the state. We want to look at, best practices, use cases, resources, lessons learned around AI. We've been doing this now for about 18 months, and this year we've decided to kind of really focus on, AI and security. Security is a hot topic, so it really is fitting, especially with what's going on right now around the world. Also, data integrity and quality, and that kind of goes off Joy's presentation, the last event that we had in December, where she talked a lot about that. We want to do more lessons learned, sharing in California of use cases throughout departments to share with other state offices. We think that there's a lot of value in knowing what's going on with other departments. And then also we want to dive into some use cases in some other states. So we're hoping to connect with some other states, see what they're doing, and have them present to us as well. So our speaker today is Micah, and he is a research analyst at the Center for Security and Emerging Technology. He is going to talk about AI and security. We're going to talk about risks, opportunities, and uncertainties. So the session is being recorded for those who just joined us. The slide deck that you will be presenting today is already on the CDT website, so those of you can go out there and take a copy of that if you want. And we are okay doing questions throughout the presentation, and then we can also facilitate a Q&A at the end. Okay? And if there isn't anything else, then I will officially turn it over to you, Micah. The presentation is yours. Take it away. Thank you.
Okay, thank you. Let me try to share my screen here. Just one moment. Let's see. All right. Just to confirm, are my slides coming through okay?
Yes, they are. I can see them.
Okay, fantastic. So I'm intending to speak for about an hour, but I welcome people to just chime in with questions as they have them. I have the chat in a separate window, so if you put a question in there, I should be able to see it. Or if you raise a hand or something, hopefully I can see it as well. But yes, so I work at the Center for Security and Emerging Technology in DC. We call it CSET. And I'm going to chat today about AI and security. There's a sort of dual component to this. There's a question of how can AI be used to augment cybersecurity, as well as what are the security vulnerabilities of AI systems themselves. I will be speaking about the latter for the majority of this presentation. It's, I think, of broader interest to basically anyone who's working in AI, regardless of what specific application they're working on. But time permitting, at the end, I'll also go through some potential use cases of AI to augment cybersecurity. Before I jump into stuff, just to give a brief overview of CSET, what we are, who we are, what we do. We are a think tank here in DC. We are headquartered as part of Georgetown University and funded by the Open Philanthropy Project. And our mission statement is to connect policymakers to high-quality analysis of emerging technologies and their security implications, with a focus on AI right now. We also have teams doing biosecurity issues and some other things as well, but a lot of what we do focuses on AI. Within CSET, I'm part of a specific team called the Cyber AI team, which is especially concerned at the overlap of cybersecurity and AI. So as I said, sort of, sorry? Oh, I wasn't sure if someone was speaking, sorry. There's a sort of dual side to cybersecurity and AI. There's both the opportunities that AI opens for cybersecurity and the ways that it could be attacked by a malicious attacker. So this is just a sample of some of the reports we've had from the Cyber AI project, looking at both the uses and the vulnerabilities of AI systems. Today, this first part of vulnerabilities of AI, I think conceptually is worth breaking down into two big components. On the former, there's this sort of AI systems, especially deep learning systems, have been studied very heavily and discovered to have certain types of mathematical properties that make attacks on those systems possible. And so in the modern AI deep learning paradigm, the sort of methods that are used to create mathematical models come with their own vulnerabilities. And that gets a ton of attention among computer scientists. People really like studying this, figuring out how they can attack AI systems. But there's also a separate set of perhaps less intellectually or mathematically interesting vulnerabilities, which just come from the fact that AI systems run on software, the same as any other type of software. And software comes with traditional types of cybersecurity vulnerabilities. And so I'll also be talking about, some of the risks that come with the AI ecosystem as it currently exists and the various types of software spread throughout it. I want to sort of suggest, I assume many people in the audience work in AI, may be familiar pretty well with at least the first part of this, but the second part, I think, receives a lot less attention. And so I'll try to emphasize some of that as well. And then again, time permitting at the end, I'll talk a little bit about how AI can be applied to cybersecurity. All right. And I'll try to build in pauses as well for questions and that sort of thing. But to start out, let me talk about the types of vulnerabilities that come with AI systems. So in the cybersecurity field, it's conventional to divide various types of security risks into something called the CIA triad, which stands for confidentiality, integrity, and availability. Confidentiality risks are risks that can disclose private information that's not meant to be accessible to someone. Integrity attacks are attacks that degrade the performance or the configuration of a system or data. An attack that alters data is an integrity attack. An attack that directly alters an AI model is an integrity attack. And then in the third category, we have availability attacks. These are attacks that are just meant to degrade the availability of a service, make it less usable, and harm a model in that way. There's a lot of research in the first two, and I'll talk through a few of these types of attacks in a little more detail as I go through. Because AI models, the summary is that they learn features from data. Sometimes it is possible to target the queries you send to an AI model in order to infer something about the data it was trained on. And that is a sort of paradigmatic example of a confidentiality attack. If you can, if a company trains a model on data that is meant to be private, for instance, you could imagine a company training like a vision system to recognize skin cancer, where you're dealing with medical images that are subject to all sorts of HIPAA regulations. If it's possible to infer things about individual people in that data set, then that's a confidentiality attack that opens up legal risk as well as just security risk. In the integrity attack, then you can sort of divide into two things here. There's attacks that might attack the data set that a model is trained on. Data poisoning attacks, where if an attacker is able to either directly access your database or if they know how you're collecting data and they can insert their own examples into that data set, you can sometimes reliably cause models trained on that data to behave a certain way. And I'll talk a little bit about that later. And input-focused attacks oftentimes try to send basically somewhat odd inputs to an AI model that trigger some sort of strange behavior that can be exploited. In addition to that three-way breakdown, you can also conceptually divide between white box and black box attacks. In a white box attack, an attacker knows everything about an AI model, including individual parameter values, the architecture of the model, the full data set of the model. In a black box attack, by contrast, the model might be, let's say, IBM's sentiment analysis tool. And the attacker knows nothing about what data that was trained on, but what they can do is send inputs to the model and then observe what sort of output the model gives in return. So those are two very different threat scenarios. In the middle, we have gray box attacks, which maybe means that an attacker has done some research and has found, this company wrote a research publication a year before they made this product, basically outlining the type of architecture that could be used to do this task. And so you can make some inferences about maybe something like the general architecture or the general place they might have gotten their data from, but you don't have full access to the model with all its specific parameter values. This is just a sort of conceptual schema for understanding the different types of attacks that AI systems can, or different threat models that might apply to different types of attacks. Some attacks might only work if you have white box availability to a model. Others might be perfectly doable under black box conditions as well. In the next couple minutes, I'm going to go over some of these specific attacks, but I'll pause here just for a second and see if there are questions about the way I've laid this out so far. Okay, hearing none. So just out of curiosity, I don't know if people want to raise a hand or put a +1 in the chat or something. How many people have heard of adversarial examples or feel familiar with what they are? Okay, relatively few. All right, so this is, I think, a sort of classic AI security thing that researchers have studied very heavily. This is an image that a coworker of mine here at CSET had taken. He downloaded this picture on the top of Georgetown University, the Healy Hall at Georgetown. And he fed it to one of the main open source AI models, I think MobileNet version 2, I believe it was. There's maybe half a dozen common image classifiers that often get used by different types of AI researchers or companies. This particular model didn't have a label for university or for Georgetown University. But when he fed this image to this model, it made a pretty good guess. It said, I'm 85% confident that this might be a castle, but it could be a palace or a monastery or something. All of those are plausible. You can see where those guesses might have come from, especially if university was not an option. But in the bottom image, what my colleague was able to do is apply a little bit of noise. In fact, it's so minor that you can't even detect it with the human eye. But just by applying that little patch of noise, this same classifier, when fed the attacked image, now believes with 99.9% certainty that this is a Triceratops. And Triceratops is not a random label. He deliberately chose that as a target label. On a very basic level, the way he did this was using a white box attack. So he had the model itself downloaded, and he could see the gradients that the model had used to train its recognition system. And by having access to those gradients, he was basically able to pick a specific target, the Triceratops label, and take a specific input and find the gradient that would move this input towards that target label, and then make very subtle adjustments to the image until the model started misclassifying it. This is possible because modern AI deep learning models just have a hugely complex system of making decisions. There's tens of thousands, millions, maybe billions of parameters, and there's often tiny maybe gaps in understanding, you might think of them as, where an image can be constructed artificially that might fit within one of those gaps and cause some sort of unexpected behavior. One way of thinking about this is maybe to also think that ordinarily, images taken of the real world tend to follow certain behaviors. There's not sudden shifts in colors except at the edge of an object. And so by perturbing the image, it maybe begins to violate some of the inherent assumptions that a model might expect to see of real world images. And that can cause strange sorts of behavior. So just an overview slide on what adversarial examples are. I basically just said that first bullet point. What's really interesting about adversarial examples is that researchers have generated these sorts of things for just about every type of deep learning model. There are audio files that can be very, very minorly distorted so that a transcription service completely misunderstands what they say. I won't play the audio, but in this link, there's actually an example. Researchers took an audio recording of Bach's, a cello concerto of Bach, and by very slightly manipulating it so that you can't even tell to a human ear, and a machine learning transcription service then thought it was speaking English text. And really interestingly, in the previous slide, this was a static image, but researchers have also found that you can manipulate real-world images in ways that reliably cause misclassifications, basically regardless of the angle that a vision recognition system might be looking at. Let me try to pull up this example here. So in one example, researchers played with traffic signs and were able to manipulate those traffic signs. Here we have a good example. Once it's a real world image and not a static picture, these attacks do tend to need to be a little more extreme so that they can be preserved regardless of the angle that a system is looking at. So you can at least notice in this image right here, let me zoom in. You can at least tell that between this 80 kilometer an hour sign here and this one down here, something's been done. There's now this, looks like purple spray paint on it. But to a common vision recognition system, this is now a stop sign and not an 80 kilometer per hour sign. And this 120 kilometer per hour sign is now a 30 kilometer per hour sign. And so this, I think the autonomous vehicle case has gotten a lot of attention because it's obviously, very worrying if real world traffic signs could be slightly manipulated. To a human, it looks a little odd, but nothing is stopping you from realizing that this is not a stop sign. And yet an autonomous vehicle might misinterpret this and cause an accident because it believes that this is a stop sign. Researchers have played with some attempts to try to mitigate this. For instance, if you have a model, you can generate a lot of these adversarial type inputs and then further train the model on that same data. So if we put this attacked image on the bottom back into our model training and we gave it the correct label, we said, yes, this is a university, or a castle if university isn't an option for our system, then that does tend to improve a system's robustness against these types of minor perturbations. But it also comes with oftentimes a sharp drop in accuracy of the overall system. And so it's not really clear when or if that method should be used to increase a model's robustness. In some cases where there's a high risk of attack, for instance, maybe you're trying to train a malware detector and you know that people are going to try to get around it however they can, then it makes sense to train on adversarial examples, even if that lowers the overall accuracy a little bit. But in other cases where those attacks aren't likely, then the loss in accuracy might not be worth it. But the system will remain a little more vulnerable to those sorts of strange, undetectable inputs that cause odd behavior. Broadly, I think it's very fair to say that there's basically no robust solution to this that machine learning researchers have identified. Consistently in every conference where this is a topic of focus, people will propose new methods of training models that accurately defend against one type of adversarial perturbation, but make the model, if anything, more vulnerable to other types of attacks. And so this is a huge issue in the security literature. One thing that also makes this particularly worrisome, I think, is that oftentimes attacks built against one model will transfer to another model, including a model that might seem to be completely different. So in this schematic, what has happened here is that you have some company who has trained a cat or dog classifier. They have a lot of proprietary data, a lot of a relatively complex model. They've trained it, and it does a very good job. But if I'm an attacker, what I might do is train a much simpler model on some public data that maybe overlaps with the proprietary data. And then what I can do is I can use my custom model where I have white box access. It's a little easier to find the minimal perturbation that causes a misclassification. And I can use my own model to figure out, okay, here's a picture of my dog. This is my family dog. If I want this picture to be classified as a cat, let me figure out what perturbation of random looking noise I can apply to this picture so that my model misclassifies it. And then if I apply that same perturbation to this company's super secret model, it may end up also transferring and causing that model to be confused as well. So this is a big issue that, for reasons that are not fully understood by computer scientists or mathematicians, models trained against one type of, or attacks developed against one model might transfer surprisingly well to other types of models. Yeah, let me pause for just a moment there, see if there are questions about that. Okay, so a reason, a compounding factor that can make this even worse in the machine learning community, it's often pretty common, more and more common now, for companies to develop one very large and pretty generalizable model and then fine-tune it on a lot of specific applications. And so, for instance, there's lots of completely open models to do image recognition. A company, let's go back to my example of someone wants to detect skin cancer in pictures of people's skin. It might actually make sense to take an open image recognition system that has nothing to do with medical images and fine-tune it on your medical image data set. Because the general model will have already learned a lot of abstract features how to distinguish edges, how to distinguish orientation of shapes in space. And you can preserve that information by fine-tuning the model on a much smaller data set. You might get better performance than if you started with your smaller data set of medical images and relied only on that. The upshot of that, though, from a security perspective, is that if you start out with that sort of generalizable public model, that might be an attacker where an attacker goes at first to try to create attacks that work against that public model. And because it will share at least some learned behaviors with your proprietary model, those attacks might transfer quite well. A second general type of attack is a data poisoning attack. In this example, we have three different scenarios. You can see at the top of each of these models, we have a hand-drawn 7 for a digit classifier. But in the bottom right corner, you can see there's a couple of stray pixels. In a base case, if this image is properly labeled as a 7, our model might just sort of learn that those pixels maybe provide some signal that this might be a 7, but it's not a big issue. We still output a 7. It's just a weird eccentricity of the data we've picked up. If an attacker has access to the model itself, they might be able to build in a sort of hardwired backdoor to cause a misclassification on this image, where this neuron here might exist just to notice, this neuron on the right might exist just to notice these stray pixels in the bottom right-hand corner of our image. And it might say, oh, if those pixels are activated, treat this image a little differently and output an 8 at the end. And so this is traditionally in cybersecurity, building backdoors in software requires access to the software itself, that you can be inserting lines of code or manipulating things in a very direct way. But in machine learning, you might not actually need that level of access. If you can change the label of this image in the data set, then if a company comes along later or an agency and tries to build a model on top of it, this model might implicitly learn that these pixels mean that this image is an 8. And so if this was improperly labeled, the attacker might be able to insert basically an implicit backdoor into your model that then they can send other types of images, and just by toggling those few pixels, they can guarantee that it'll be output as an 8. Data poisoning attacks are, they do require the ability to manipulate labels in data sets oftentimes. But researchers often, I think, use the 1% threshold as basically the challenge is how much access can you get to a model to cause it to misclassify things if you can only adjust 1% of its data. And I think usually the answer is you can do almost anything with 1%. You can build all sorts of these backdoors in so that you can know that if I send an input to this model with some specific feature, I know that it'll behave in this way. Again, as an example, a great example is maybe a malware detector, right? If you can make sure that some companies' antivirus software, if you have like a certain string of characters in your source code, it'll treat that as benign, then that gives you license to just put that string of characters into any piece of malware and have it slip by the detector. And finally, yeah, I think for the sake of time, I'll skip over this and I'll say just some overall thoughts on some of these sort of mathematical attacks on AI systems. The use of pre-trained models and fine-tuning, I think, dramatically increases the risk of transfer attacks working. But this practice is more and more the norm in AI. It's common, I think now, more and more common for companies or researchers to create some very big generalized model that then gets used for dozens of downstream applications. This is especially true maybe in the natural language space, where there's lots of models now with, even several billion parameters just available that people can download and play with for themselves. And so if you want to create a model to, say, read legal documents, you might start with one of those models that already has some understanding of English language and then fine-tune it on legal documents. But that practice means that attacks that work against the pre-trained model are likely to transfer to your final model as well, or at least they're more likely to do so. Another huge issue is that these models are just too complicated, and the input space is too large to comprehensively test all the types of things that could trigger a robustness failure. The researcher community, I think, is really scratching their heads right now, trying to figure out if there are any generally applicable rules that can mitigate these risks. Further training your model on adversarial examples seems like one that does sort of mitigate some risk, but as I talked about earlier, it might also degrade your overall accuracy. And many of these attacks, because they're sort of mathematical in nature, they do take someone with at least some fairly in-depth understanding of how AI systems work to pull them off. But certainly not, out of the reach of a ton of people. It can, this adversarial example that my colleague created was created in, I think, about 2 or 3 dozen lines of code. So it's not insurmountable. You just have to have, a clear idea of what you're doing. And it's possible that in the future, there might be prepackaged ways of generating these types of attacks. I'll pause again just a second before I transition into part 2 of this talk. I'm a little over on part 1, so I'll try to speed things up a little. Okay, so in the second part, I'm going to talk about. I hope that gave you a bit of an overview for some of the attacks that are commonly discussed among computer scientists, ways of attacking AI systems. In this part, I want to sort of back up a half step and talk about other ways that you could attack AI. So here we have a sort of supply chain for an AI model, a sort of nominal, fairly common, I think, conceptualization of how an AI model comes to be. We have this pre-trained model type situation where there's a large generic data set that was used to create some generalized model, but that model can be further trained or fine-tuned on an application-specific data set. This results in a more specialized model that an agency or a company can make accessible to users through some sort of interface. And the attacks I've talked about so far target different parts of this supply chain. Data poisoning attacks will try to slip something into one of these data sets. A transfer attack might start with a pre-trained model and try to find an attack that works against that to then see if it works against the more specialized model. And through the user interface, people can launch black box attacks if they can't see the actual model itself. So this is sort of what I've covered so far. I think this is a common picture that a lot of machine learning people have in their mind of what the components of a leading up to a model are that could be attacked. But I think this is a little simplistic. And so here I have a slightly more complex version, these green additions try to acknowledge potential targets that don't exist in the previous slide. So this data set and this pre-trained model, they don't just exist, they exist somewhere specific. Someone is hosting them, a company or a website. With language models, maybe it's Hugging Face. They host a lot of models. And that hosting infrastructure is going to be built up out of software that is maybe manipulable. It could have, pretty traditional cybersecurity vulnerabilities that if you can sneak behind, you can do all sorts of strange things. It's also the case that you don't simply step from a data set to a model. You need algorithms and code to actually implement a training process. Oftentimes something like TensorFlow or PyTorch are common machine learning libraries. Those are made of code, and code can have vulnerabilities. And they might depend on other libraries too. NumPy, another Python library that might be behind the magic in some of this. NumPy I mentioned specifically because this is one where actually vulnerabilities have been discovered. For instance, a few years ago, it was discovered that the load module in NumPy that could load in a machine learning model from a file somewhere actually could be used to execute arbitrary code in that file, which meant if a user got a file that looked like it contained the parameters for a machine learning model, and they tried to load that in, they might be inadvertently giving an attacker the ability to execute any sort of malicious program on their computer. And so, there's this more extensive supply chain that is just, the broad point, I think, is just that it's made up of software, and that software can have vulnerabilities. And even very trivial decisions, or decisions that seem trivial to a machine learning engineer, can also be exploited. And so there's a lot of formatting that goes on. This is another one that another colleague of mine played with a little bit. Most machine learning models, I'm sticking with vision recognition here, they have certain assumptions about the data that they're going to process. And especially a machine learning model usually expects an image to be the same size as all the images in its training data. Obviously, like anyone who's ever uploaded an image to like one of those AI art tools or something knows that usually in deployment, an AI model doesn't ask you to resize your image until it's the right number of pixels, because there's a little pre-processing step that does that for you. One way of doing that resizing is with something called bilinear interpolation. It's just a method of, in this image example, we have a 5x5 image that we're trying to resize to a 3x3 image. And so what this step will do is it will calculate, if we expand a 3x3 grid out into a 5x5 grid, where do the centers of that 3x3, each pixel in that grid, where do they fall in our larger image? And then we can sample 4 points surrounding that target point and average them together to get our resized pixel. This seems, like a relatively straightforward way that you can take a 5x5 grid and reduce it to 3x3. But it turns out this can be targeted in its own way, because what this means is that for any target pixel in your resized image, you can sort of calculate backwards which exact 4 pixels in your input image the model will look at in order to find that new pixel. And so a colleague took another attack where He took, again, a nice, large, very detailed picture of Georgetown. That's 3,000 by 4,000 pixels. And he attacked another common vision recognition system that requires images to be 299 by 299 pixels. And he was able to calculate, for each pixel in this smaller version, which 4 pixels in my big input are going to be sampled to generate the new pixel. Because if you can manipulate those, you can change what the image looks like when it's resized. So this attacked picture of Georgetown, when it's resized to exactly 299 by 299 pixels, it actually is a Triceratops. And so if a model now says that this picture is a Triceratops, the model is actually doing its job correctly by saying that this is a Triceratops. But a designer may have overlooked that what they think of as the input to the model, which is this thing before the pre-processing step, is not actually the input to the model. And so this creates its own vulnerability. Let's see. I just noticed a question. Most machine learning pipelines are fronted by an API or app. Can bad input data be filtered there? Yeah. So this is a sort of question where it depends, because it depends on what you know to look for. So where I'm actually going with this one, with this example, is that there's an easy defensive strategy, which is don't use this simple method of sampling only 4 pixels. If instead, for a target pixel, if instead of only looking at 4 pictures, we use a method called 4 pixels, if we use something called anti-aliasing and we look at the whole region of surrounding pixels, weight those different pixels differently, and then use them all to figure out what our target pixel should be, it's no longer possible to do this sort of attack. And so this is actually a really, it's a fun attack, but it's actually very easy to defend against, unlike the adversarial examples I talked about earlier. The wrinkle, though, is that if you look at the, every machine learning library has some sort of resize function for images. And if you look at the different resize functions for PyTorch, for TensorFlow, and for scikit-learn, 3 of the common libraries, they all have an option for anti-aliasing that is disabled by default. So in TensorFlow, anti-alias is set to false by default. In scikit-learn, anti-aliasing is set to none by default, and same for PyTorch. And so what this means basically is that if an engineer knows that this is a possible attack, they're very lucky, because it's very easy for them to adjust against it. They just have to pass true instead of false to this function when they use it. But the problem is, or at least from a security perspective, the problem is that this is not the default. Using this wider sampling does make images a little bit fuzzier. It takes, just a millisecond longer to do the resize. And so machine learning engineers, who oftentimes think in terms of efficiency and in terms of overall performance, to many of them in their mind, the default makes sense to be false. And from a security perspective, it's sort of, I'll say it's a place where the default is not very security sensitive. If someone wants to defend against this sort of attack, they have to have the implicit knowledge that it is possible in order to mount this sort of defense. So this is not a direct question to my answer to the question that was posed in the chat is that bad input data can actually be filtered, some of the time at least, but you have to sort of know what you're looking for. And so a lot depends on whether or not some of these filtering tools are in place by default. And at least in this case, it's an example where that default security setting does not exist. It's something that engineers have to know of their own initiative in order to defend against it. Let me pause there again and ask if there are other questions, or if there's a follow-up question to if Amran has a follow-up. Okay. So moving on, I'll do. This will be, I think, a little brief, but I'll switch gears a little bit now and talk about, well, okay, how can AI be used for cybersecurity? In a broad sense, deep learning has been around maybe for only about a decade that it's been a major area of research, but machine learning more generally has been around for some time now. Especially in the area of supervised learning, where you have concrete labels for your data. And from a cybersecurity perspective, one natural place to use supervised learning is for types of detection tasks, spam detection, malware detection, intrusion detection. These are all common places where it makes sense to use supervised learning. So each of these has actually been around. Machine learning methods have been in use for over 20 years for these different types of cybersecurity tasks. And one thing I think, it's hard to say this with a ton of confidence because I can't see the internal metrics that cybersecurity companies use or that Google uses to monitor their spam filters. But in general, I believe it is the case that with the rise of deep learning about 10 years ago, there was a sort of qualitative improvement in how these detection tasks worked. Systems got a little better at detecting attacks, but it hasn't necessarily completely transformed things. And part of the reason for that is that in cybersecurity, given the rate at which the number of attacks has expanded, you have a sort of a situation here where even pretty rapid improvements to performance on a detection system might end up only keeping pace with the growth in attackers and the variety of attacks. So it's an extremely hard field to solve. In general, there has been some, I think, general descriptions here is that you have a distinction between network-based intrusion detection systems that try to monitor a whole network at once versus host-based systems that monitor an individual machine. Machine learning, you might expect that over a whole network, individual variations sort of average out, and so it's easier to detect something going wrong. That turns out to not be the case. It's actually the case that machine learning tends to do much better monitoring for intrusions on individual hosts. And so in that sense, I think machine learning has accelerated or is accelerating to some extent the adaptation, the adoption of zero trust mindsets in cybersecurity, where instead of trying to think of networks as a cohesive entity where there's a clear perimeter between the outside and the inside, instead, cybersecurity professionals want to monitor each individual machine on some level and not assume that the network as a whole is either compromised or not, but rather assume that at any given time, some part of the network might be compromised. There's also different breakdown of some machine learning methods are used to identify attacks based on known attack patterns. Attackers oftentimes will change their malware a little bit, but they might be launching similar types of attacks over time that contains at least some repetitive code. And looking for those sorts of attacks, matching to a known profile is called a misuse-based detection system. In contrast, there are anomaly-based detection systems that try to be agnostic about what a particular attack could look like, and just say, you know, we're monitoring for anything that looks strange. This has been the gold, you know, the peak goal in cybersecurity, because this lets you identify zero-day attacks. Attacks that are completely novel, where there is no known profile. But again, you know, sort of disappointingly, it turns out, I think, that machine learning models still struggle with that, and so have been a lot more used for misuse-based attacks. I also have just a few examples of some, I think, you know, fairly interesting use cases of AI in cybersecurity. So there's one here. I've taken this from a Microsoft blog post about Azure Sentinel, which is a product that Microsoft uses to monitor for intrusions on a lot of its cloud products, I believe. A huge problem in cybersecurity, and machine learning by default doesn't tend to help very much with this, is that there are lots and lots of potential intrusions. Most detection systems generate just a tremendous number of false positives, things that could be an intrusion, but without further investigation, it's not conclusive. And this is especially a problem given the current shortage of cybersecurity skills, that cybersecurity professionals feel very overstretched. And so if you give them a system that can identify attacks, but also generates a lot of false positives, they, in practice, very quickly learn to tune that out. What Microsoft did to address this is, instead of using machine learning to generate the alerts that an intrusion could be happening, they realized that machine learning could actually do a very good job of ranking those potential alerts and you know, looking for patterns in the time between a series of strange behaviors, and generating graphs to represent a sequential order of actions that an attacker may have taken, and then learning which of those graphs and which of those profiles are indicative of a potentially novel attack system. This was this graphic is from a report in December of 2019. They generated over 50 billion alerts, which obviously is too much for a team of almost any size to follow up on. But using actually a tiered system of machine learning, they were able to winnow that down to 25 attacks that emerged from this massive set, and that looked very novel. I think this is a good example because it shows, you know, that there's actually this tiered structure of using multiple types of machine learning models to accomplish something. A second example, there's been some experiments with using reinforcement learning to simulate decisions that a defender might take in response to an attack. This is very briefly, what this entails is trying to simulate a network, simulate an attacker, and then give a machine learning model the ability to make certain decisions, like when to disconnect a machine from the broader network, or when to re-image it or patch it. Reinforcement learning models can sort of learn the right risk-reward trade-off for when to take those actions in response to something that could be an attack. The problem with this approach is that reinforcement learning requires a really robust simulation of an environment, and it's very hard to simulate computer networks, especially at the scale that most modern organizations work at. It takes a huge computational cost. It's not clear how well these strategies will generalize from one type of network to another. So this is an area where I highlight it as a potential future area of interest, but somewhere that's still sort of in its infancy in the research community. And one final example, just worth mentioning, back in 2016, DARPA hosted an event called the Cyber Grand Challenge. It was a competition for teams to develop systems that could autonomously find vulnerabilities and then either patch them or exploit them. And this is worth mentioning. There's been some thought that machine learning can make this sort of automated vulnerability discovery more efficient. There are some research. This first bullet point links to a paper that says, yes, it's more efficient than naive automation. But at this DARPA challenge, it was actually the case that the winning team used almost no machine learning to identify vulnerabilities in code. Instead, they just spent a lot of time very carefully, trying to create an expert-based system. 2016 is now 8 years ago, which, to machine learning is vastly out of date, but very few similar competitions have been run since then. So this is, again, just a sort of question mark where it makes sense on some level, I think, to expect that machine learning could be great at finding vulnerabilities in software, maybe even writing patches for them. But it's unclear how far advanced we are there. And at least as of 2016, it was the case that machine learning was not really a major tool of use for this. Another question in the chat: how would you protect a real-time reinforcement learning model against an attacker swaying it? Yeah, that's a fantastic question. This is certainly a problem in reinforcement learning, that if your adversary makes unexpected moves during actual deployment, your model might completely misreact or misunderstand. What I will say, I guess, is that this is also, I think, just a sort of general nature of cybersecurity, that attackers are always looking to confuse or to sway the defenders. There's a lot of opacity in the environment as people engage with each other. And so if a reinforcement learning model could be trained that was more robust to being swayed or confused than a human, then that would be very big news. But humans are also susceptible to the same types of attacks that you might launch against a reinforcement learning model. I'll wrap up there. Right, almost an hour on the dot. So I'm quite pleased with that. But we can. Let me also end my screen share, and we can see if there are other questions.
Thank you.